All right, can everyone hear me? Awesome. Usually I like to start things off with a little bit of a joke. I had a hard time coming up with one tonight. The best I can come up with is I'm a skilled AI developer. Anyway, this presentation was not made with AI. Instead, we're going to be talking about containers without Docker. If you're here for Podman, you're in the wrong group. You're not talking about Podman. Well, we'll learn about how Podman works, maybe, but not really. Okay, well, I'm Fred. I work at Cloudflare as a systems engineer. I do performance analysis, security analysis, and then also systems programming, as implied by the job title. Why are we talking about containers without Docker? This all started when I needed to perform some sort of test. I was trying to do a performance analysis of the connect syscall. For those that aren't familiar, connect syscall is what's used whenever you make like a curl request or any sort of connection through the browser, wherever, to some outside internet, or even internal, it doesn't matter. Point is, it exists on Linux systems, and I was trying to get the performance characteristics of this syscall. So I wanted to open up as many IPv4 unicast TCP connections as fast as possible on my machine without breaking my machine. That is a mouthful. So let's actually break it down into what the requirements actually are. So I need a client that needs to be able to connect to a server. The system must be configured to actually open up 56,000 ports, which is quite a lot. And I needed the connections to be load balanced over several IP addresses for my testing. And then finally, I needed to have some pretty way to report the latencies involved. Essentially, I wanted this end result, where one algorithm performs way better than another. In case it's not obvious, the one on the left, no, right, sorry, is the more performant algorithm. So that's what we're trying to do. And the way this works is we essentially create a socket to bind it to a port. That's what the client must do. We need to configure our system, and this is done through a tool called sysctl, sysctl, however you want to call it. It's a tool in Linux to configure Linux, essentially. We need to increase the unit limits. So in Linux, ulimits are very important for your process to know how many files it can open up, for instance, at any given point. Spoiler alert, we're going to be opening up over 1 million files, but not really, just 50,000 of them, but still quite a lot, more than the default. We need to create a network interface on the computer. So this is if you ever type in IP address A or something, and it shows you a list of like all your available IP addresses or things like that. Those are all your network interfaces. We're not going to get into too much of that tonight, but we need to make one of those ourselves. And of course, we need to be able to create IP addresses and assign them to these network interfaces. And then lastly, everyone needs their little favorite Python libraries to make everything nice and pretty, right? But there's a problem. To do any of this stuff, we actually need root permissions, and that's kind of like where Docker kind of fits into this problem. Docker is really composed of two like discrete, separate concepts. Oftentimes I find people kind of conflate the two, but really when we're talking about Docker and being able to ship environments, we're actually talking about the Docker images themselves. So these are system independent. You create a file system with them, and you can share them with your friends. You can put them up on Docker Hub, whatever, right? You can just put them wherever you want. They're composable. So I'm not going to get into the OCI spec tonight, but they're composable, so you can layer different images on top of each other to make one final image. And it's all done at build time. But then we have the concept of containers. So containers are actually the runtime of these images. So they are system dependent. So tonight we're going to be focusing on Linux, but if you want containers through Docker on Mac or Windows, it actually runs through a virtual machine. These containers use these images to actually like execute programs or whatever you want with inside these containers. These are non-shareable. Now, if you actually know what I'm talking about tonight and come across me saying non-shareable, this talk is not for you. But we're not going to get into that tonight, but for all intents and purposes, what I mean by non-shareable is I can't just pick up a container and give it to you on another system quite like I could with an image. Horizontal scalable, so you can put up a lot of these things right up next to each other and have them do all fun stuff like, Levi here loves Kubernetes, so this is Kubernetes for you, right? So containers actually happen at runtime. So the promise of Docker is you write your environment once and you ship it everywhere. So let's actually apply this to my particular problem. So I'm going to go ahead and create my Docker image. This is the typical way to make Docker images. You have this from whatever blob at the top that basically says, I want this base file system to be like what this image is going to be based off of. You're going to run your little apt-get updates, apt-get installs to install whatever kind of programs you want this container to have or to actually use with the image. And then an entry point that when you actually launch the container, this is what actually gets executed as the container part of the container. I'm saying container a lot, but bear with me. So the way this builds is you run this little command, docker build, you pass it in the image name and what your tag is, and then you give it the file that builds this image, and then bish bash boosh, Bob's your uncle. So on my computer, when I run a grep pretty name on my OS release, I get back Ubuntu. And to kind of drive the point home of you kind of what I mean by ship environment anywhere is when I run this container, we actually get a different Linux distribution, Debian GNU Linux, bookworm. So that's kind of the promise of build your environment, ship it everywhere, right? So let's apply this even further. So this is my test script that I want to actually run. It's very basic. Basically what I'm doing, I said, okay, ID means give me my current user that's executing. ulimit, I'm setting the actual limits that this process is going to encounter. So I'm increasing them from I'm increasing the default small limit to the high limit, so that way I can basically blow up my machine essentially. Perform the sysctl to basically tell the Linux kernel to give me this many ports to be able to allocate, but there's like strict defaults there. And then my little Python script that generates the data, runs the performance analysis, and gives me my results, right? So then we actually build the image. Did I duplicate slides there? No, I did not. Okay, sorry. I reordered the slides right before I came here tonight, actually. So this is what the container image is actually going to look like in this case, right? So again, we start off with bookworm slim, do my little app updates, copy in my actual test files, so the generate Python script, runner script, and then I just run it, right? Wrong. I don't run this thing because what ends up happening is my ID does show me as root, but if we go all the way down to the sysctl, what do you mean permission denied on key, blah, 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 blah. What are you talking about? I'm root, right? Right? No. So the problem here is we actually run into a capability issue within the kernel itself. So just a quick call out, whenever you see $C in front of a command or whatever, that means that this code was actually executed within a container. So I went into this Docker container, I got my current process's status and got my effective capabilities, and it prints you out like this little nice hexadecimal number that you can decode with this tool called capsh, and it lists out all the capabilities that this process has. But we're missing the two key capabilities, capnetadmin and capsysadmin. Capnetadmin is used for actually creating networks, interfaces, actually, and all that fun stuff with resource allocation for networks. More on that later. And capsysadmin is your actual system level root privilege. So if you are on Linux and you have capsysadmin, you basically have the keys to the kingdom, essentially. This can be fixed. So usually the way Docker works is that, I can't, usually my slides would show up here on the screen a little bit bigger, but, okay, so so basically the way Docker works is that it runs containers through a process called containerd. Containerd is a daemon that runs runc, I know it's cleverly named, which is the runtime of the container. So containerd you can think of as your orchestration tool. So you tell it to say, hey, I have this image, go make me a container. Runc is the thing that actually makes the container. But here's the kicker. run C applies seccomp policy by default. And also, it has default capabilities that it runs your containers with. So in my example prior, we can see that even though I have root, I'm effectively the root user, I actually don't have the root capabilities that I'd expect when I actually run this container. So these must be overwritten to solve my particular problem. But the interesting thing is that containerd is a root process. So there is we can kind of see that there is like some security baked into Docker by default, right? More on that later. So to hell with Docker, let's make my own container. But before we can do that, we really need to talk about namespaces. So in Linux, containers are actually namespaces. So namespaces are a Linux kernel feature that allows you to isolate and manage process resources and isolate processes from one another, from the host and each other, okay? So when we talk about containerization, what we're really talking about is process isolation. If you ever get asked what the difference between a container and a VM is in an interview, this is it, it's process isolation. And namespaces have many different flavors, and tonight we're only going to focus on a few of them. The mount network, process ID, Unix time sharing, which is kind of the funny named one, and then user namespaces. There's also 3 others, control group, interprocess communication, and time. We're not going to cover those tonight because they're kind of all in depth in their own presentation anyway. But when we talk about Docker, what we're really talking about for most use cases is mounting file systems and creating networks, controlling your processes within your containers, and then Unix time sharing, we'll get into that, and then the user namespaces. So to kick things off, how do we actually make containers? So we have a few ways to do this. So all these tools, clone, setns, unshare, these are all syscalls you can actually use like in your actual programming code. But a couple of these are actually like tools that come with Linux itself that you can run on the command line. Specifically tonight, we're going to be talking about unshare. And then we have other tools too to create containers, obviously Docker, Podman. You can even create containers, networking containers, at least with the IP command, netns. And then of course, finally, systemd nsspawn, which we will cover at the very, end of this presentation. So, before we move on, to demonstrate this, echo $$ basically says, give me the current process's ID. Okay, I'm going to run unshare, and now I'm actually in a container. So my process now got container, so it has a new process ID. And then when I echo its PPID, which is the parent process ID, we can see that's the same as the one that I just unshared into. So basically what this demonstration here is that I'm on a bash shell command terminal, whatever you want to call it, and I've just created a container. It's that simple. Okay, now we're going to dive into the details a little bit. So user namespaces are really powerful tools. So these are used to isolate capabilities among your processes on the system. You can also map users to other users' capabilities. And I have a demonstration of this with the proc-self user UID map at the bottom there, where basically I'm saying I'm going to map my user 1000 to the root user 0. And the 1 just means that this is happening for one user, and it's just that user ID 1000. Okay, so user namespaces, we map our process capabilities to other users, and in this case, I'm mapping it to root with the onshare --map -root. And when we run ID on that within the container, we can see that we are effectively root. But here's the difference, though. If you recall from the other slide, the cap for our process actually is now basically all filled out. It basically has all ones, which means that this user actually has all the necessary capabilities we need to actually perform my performance testing. This is different from Docker. So, like I said, when you make your own containers, you have full control. But there's a controversy. Everyone loves user namespaces. Why do we love user namespaces? Whenever you see that headline Linux kernel vulnerability, CVE, you give it a number, guess what they use to get in your system? User namespaces. I've even used these to exploit Linux systems in the past too. But the thing about user namespaces is that they are actually a security feature, which is kind of ironic. The only thing that makes them dangerous is that if there's a kernel vulnerability, user namespaces can be used to expose that. But really, user namespaces are great because we can actually, without needing to be root, we can actually create kernel resources for our tools so we don't actually have to become root and actually become a real security problem. Does that make sense? You don't actually need root, right, to actually have root privilege and root accesses and don't need to like ruin your own computer. But I don't know, there's a controversy with it, but I want to make it very clear every time I give this presentation, always someone says like, wait, user namespaces, they're the devil. No, they're not the devil. Not the devil. Okay, moving on. So to drive this point home that you only have root capabilities does not necessarily mean that you have root file system capabilities where you can actually perform dangerous operations. So when I am in this container, even though I am root, when I try to create a file in the root directory, I can't actually create it because I don't have the permissions, okay? But if I create it locally, it is created with the root user. Weird. But if I get out of the container and then I stat that file, oh wait, it's actually created with my user permission. So the thing about user namespaces is even though you're mapping your user capabilities to another user's capabilities, you still actually have the same file system permissions and things like that of the parent namespace. In this case, it was my user's parent process, which could only create files with that ID, etc. Okay? So let's bring this into Docker. So when we run, I have this like very trivial entry point to run unshare this Docker image, but the problem is when you actually run this unshare within it, it actually fails. We can see this with a syscall trace tool on the containerd process. When I actually try to run this container, we find out that when you try to run unshare, permission denied. Whoa, what's up with that? So, like I said earlier, Docker has built-in ways to kind of protect you from actually exploiting the kernel through unprivileged processes. And this is not to be confused with Docker run --user. No. That's totally different. That just tells Docker daemon to run your process as that user. It has nothing to do with user namespaces. But if you actually want to use user namespaces, you have to configure Docker using the user NS remap. But I don't know if that's changed since I last made this slide. So if you actually wanted to use Docker with unshare, you actually have to up the privilege of your container to actually be root to use the unshare command. And the problem with that is once you give Docker this level of root, you have to remember when you have your images, those can come from anywhere. When you create your Docker images, those can have programs from anywhere. They can have their own vulnerabilities, their own exploits, you name it. But if you run your containers with privilege mode, you're basically saying this container actually is root now, like is literally root. And it still doesn't use clone new user to achieve this. This is just the Docker containerd process saying, hey, look, give this guy root. I don't care. They trust it. Okay, whatever. We'll drop all security policy, right? And with this mode, you can actually access system level resources, and it's super dangerous, right? End of the day, you don't want to do that. So, in summary, each process has a user namespace by default. So when you actually unshare into a new user namespace, you're actually inheriting the permissions, file system permissions from the parent namespace, in this case my user. You need it for system security reasons if you want to have root capabilities without actually having to elevate yourself to be root. File systems respect the original user, like I already mentioned, and it's not used by Docker by default to run containers as different users and things like that. But now the fun one, right? Unix time sharing. So this one's kind of goofy. Have you ever made a Docker container that has some sort of MySQL server or something like that, and you give it like a cool little host name or whatever? This is literally the namespace that you use for it, the Unix time sharing one. Why it's called Unix time sharing is kind of historic, but the idea is that this a process's effective name, not your username, but the process's name is now whatever you choose it to be. And in this case, I went ahead and in the container, it by default grabs my host name. and then I could change it to container, and then when I change the host name to container and run host name again, it's now container. This is literally the whole point of this namespace. There's nothing else to it. That's literally it. It's kind of funny, but you know, Kalse agrees with me. He likes being hostname.com. That's how you do with Docker, by the way. Ooh, networking namespaces. This is like the most crazy namespace of all of them. We're not going to go into too many details about this one tonight, but the essential idea is that in Docker's terms, you create this with the network property, and the thing about network namespaces is that it's very well used for network isolation, and I have some more examples in future slides. So to kind of drive this point home, if we go into my little container, I see that if I run IPA, my interface, my loopback interface, is actually set to down right now. So if I try to ping it, network is not reachable. But I can actually set the link to be back up, and then I try to ping some outsourced IP address. Wait, nope, I can't actually do that because this container is isolated from the host. So if you want to set up networking to be inside your containers, you have to set up another namespace and make the two talk to each other, things like that, to make that work. But otherwise, if I wanted to talk to my internal interface, my loopback interface, I can ping it all day long. Which, yes, this is a more complicated example. So my colleague, brilliant person, wanted to use a tool called Mark to use translate basically Markdown into a Confluence page. But the problem is that it used an HTTP client in it, and he's like, no, I don't trust that. So he created a tool called CF Access Proxy, which, as the name kind of implies, he isolates the tool inside of its own container, and then we apply our keys and tokens that we use to talk to our Confluence to get access to it outside of that container. So if anything is running inside that container that is not meant to go out to the to the actual wiki, it'll catch it, we'll let it run. Brilliant for isolation, and this is like a really complicated setup. But the brilliance of this is the sharing of the socket file descriptor here. I'm not going to show you the code, but the point is, this is like really cool use case for network namespaces and namespaces in general. Is this level of isolation to protect your host computer from nefarious software that you may want to run on your system, and also even apply keys and tokens that you don't want to expose to it as well outside of that container. Yes, this does mean you can actually create containers, not just with a shell like I've been demonstrating tonight, but also with your favorite programming language. C, Go, PHP, Python, Rust, etc. Maybe not JavaScript. Probably not, but but I have good authority that Google Chrome does use namespaces, so there's that. At least that's isolated. Moving on. Process ID namespace. So this one's like really cool too. The idea behind it is that it makes your process effectively PID1. Now, for those that are not familiar with PID1 in Linux, basically, whenever you boot up your computer, it boots up the kernel, it gets you into user space, yada, 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 but then something magical happens. It actually runs user space. This is your PID1. So in most systems, this would be like systemd or whatever your init system is, and that is what's responsible for basically whatever you want on your machine at that point. Load up a terminal, do whatever you want, load up new processes, yada, yada, yada. But here's the thing though, this namespace allows you to do that, but within the container itself. So when you actually run your Docker containers, they may actually be running as PID1, and then whenever you spawn a new process within them, they're relative to that process. So we can kind of see here that in my little container example, I fork into my own PID process. I'm in the container, I run psax to grab like what's being listed there, and we can see that the first PID that's there is this actual terminal shell, and then when I echo with that out, the $sign, we get 1. So this process is actually considered PID1 as far as Linux is concerned. Now outside on the host, it just thinks that this is process ID, whatever the hell it was when it first started off as, but within the container, the host thinks this is process 1. Neat. This comes up later, but neat. And then finally, we need to talk about mount namespaces. So the way images work is through the mount namespace. And the cool thing about this is it allows you to set up different file systems and isolate those from your actual host too. So again, name of the game is process isolation. So these are typically your root file systems, and you can move your files in between here and the host with these mount namespaces if you configure them correctly. And it kind of looks like this in Docker land. We create a little volume, and then we do some entry point magic within there to output something to that volume. And this volume is created on the host, and then this Docker image is going to bind to that volume and then write something, and then write a file to it. And then when we run it, what we get is, well, I guess before we run it, we actually need to make the directory. Then we create the volume outside the image, and then we tell the Docker command to actually mount and then use that volume as that link between the host and the inside the container to actually leverage that volume. Now we run it, and when we actually look at the file that comes out of it, we can see that that actually ran, and the calce ran. It wrote the file to my local. It wrote the file to the host under calce-mount/calce. But here's the interesting thing. Notice how the root, or how the user and group is actually root. So, like I said before, Docker is still running as root. Your containers are still running as root, so it created this file as root, which if you ever had any issues running Docker on your machines and had file system permission issues and all this other stuff, this is it right here. It's all because of this. It's all because your volumes and the Docker images and containers themselves are all running as root. So here's what it looks like in bash land. We use the unshare map root mount. And then now I'm in the container, so I create a mount. So tempfs is like a memory-backed file system for Linux. So I create that memory-backed file system with the mount command, and then I use mount pipe grep to prove that it's actually there, and we can see that it is there on that actual mount point, which is that directory I created. And when I list it out, there's hello container in it, I guess. But then on the host side of it, when I actually run cat on the file, whoa, it ain't there. It's not there. What happened to it, right? This is not what I was talking about earlier with Docker, right? Well, see, again, so we're talking about, I didn't do the rigmarole to set up all the volume mounting in this case right here. I'm just trying to show you that when you actually run mounts within your own namespace, when you create them, the host has no knowledge of this stuff. Only the container has knowledge of this stuff. So this is like a nice little way to also keep privacy, security, and things like that isolated to the process that's actually running these things. So yeah, my host has no idea that this even exists, but it's there. Okay, so how do we actually implement Docker images in the command line? Yeah, more on this later. It can be quite complicated, but yeah, more on that later. So in summary, mount namespaces used to isolate your file systems on your container processes. It's great for keeping the host no knowledge. It doesn't need to know about it, or if it can, or if you wanted to, you can. World's your oyster on that one. It's a powerful tool to share mounts with other containers and hosts, like I just said, and there's whole presentations dedicated to this subject. But I think the really interesting thing here too is that even though when you create a mount namespace and you create your own mount within it, it still has access to the host. Like in these trivial containers, like it still has access to all the host mounts as well, but the host doesn't have access to its container mounts, right? So that's kind of like the key difference. And there's ways to like finagle this, which we'll show later on how to like completely replace that within the container later. And then I know I said I wasn't going to talk too much about control groups tonight, but I thought I'd give like a huge shout out to them. So the nice thing about control group namespaces is that control groups are used to assign resources to processes within your system. So you can assign processes specific memory limits. CPU time, execution time, things like that. That's all done through what are called C groups, control groups, and there's also a namespace to do that too, but that's out of scope for this talk. So we're gonna tie it all together. I need a drink real quick too. Read the code, enjoy it, internalize it. Okay, cool. So what's happening here? So the big difference between this and the initial script is I went ahead and used the unshare right before it, and then used this, and then created a script on the fly to use as the init file for this container. So basically this is the entry point, if you will, of Docker. So it's the same code. I'm going to set -x, which will output each of the commands one at a time. I'm going to set up the loopback device. I'm going to set my ulimits, and I'm going to run the sysctl, and I'm going to run the code. And I didn't include a mount. Why? Well, like I said earlier, I don't actually need my own image for this test case. All these tools that create all the pretty pictures and what already exist on my host machine. So why do I need to create an image just to do that, right? So when we actually run it, holy crap, it actually worked. This is where you applaud, right? Like, you know, we have some performance analysis here, right? Yeah. All the connections, they did exactly what they needed to do. Oh, no, but you know, if you thought we were gonna end there, no. We're gonna kick it up 10 times. All right, so, which is kind of ironic because I was actually debugging systemd today too. So, you know, this is actually pretty timely. So, systemd, as a quick refresher, systemd is the PID1 of your Linux operating system. In fact, there's a meme these days that your operating system is no longer Linux GNU. It's actually just systemd. I mean, it's kind of true, but you know, like when you boot up Linux, the first thing you see is like all these services starting, all this yada yada yada. That's systemd, right? So it runs as PID1 on your machine. So if PID1 ever breaks on your machine, right? What do you think happens? Can you still use your machine? I see some people shaking their heads no, right? Actually, you can still use your machine. Systemd has protections for this, but you can't tell systemd to not work at all if if you want to. Ask me how I know. Okay, so, but the TLDR is you don't want this process to break. So how do you actually debug and run systemd? Well, you could traditionally spin this up in a virtual machine, create your own little file system for it, you know, takes forever to do, or we can actually use containers to do it. In fact, we can use systemd to debug systemd. So let's talk a little bit about how that works. First things first, you absolutely do need a file system image of some sort. So in this example, I'm using a tool called mkosi. You can pass in different parameters to it to create a Ubuntu file system, a Debian file system, an Arch file system, Fedora file system. You name a file system, this tool basically does it. And you can tell it to install these packages as it builds this file system. But natively under the hood, you would often see like tools like mkarchroot from Arch to build Arch file systems, or Bootstrap to build file systems. But like I said, if you wanted to do multiple different distributions, you could just use this tool, mkosi. Or you can even download raw images and extract them from the distribution. So they also release this stuff online as like cloud images, raw images, you name it. You can just download it and use those directly. Or even better, you can create your own Docker images and then just extract the file system out of that too, as another approach. But the big point is that these tools all exist to basically do what the from, I don't know what to call it, what the from thing does and Docker images does, which is to basically grab a file system on hand. So all this work just for that, right? Crazy. Well, maybe not so much. So moving along, in order to further set this up, we need to have like a build directory for systemd. So if you have, after you've cloned the repository and done your changes, you need to then install it into a specific directory that you're going to run your new changes from, and you're going to create your own little config maybe your own little config file system to set up some additional settings for the system when you actually boot into it. So in this case here, I'm creating a little auto login configuration file that basically says, hey, you know, when I log into systemd on my computer, after this point, I don't need a password. I don't even need a user. Just put me in root. Just get me in there, right? I want to test stuff, right? That's basically all that means. But the general idea is that we're doing something very similar to Docker. We are composing file system images one on top of another. More layering going on here. I created a make file. I put in all my little testing into a different directory on my file system, and it does this, right? So basically, I'm just trying to show that we're composing our layers, and this is the equivalent of that runner.sh file from earlier, right? We're composing our layers of tools that we actually want to execute inside of a container. But then we overlay it. So when Docker does its mounting and does its imaging, it's doing this. It's basically taking each of those file system components and then it's layering them one on top of another. Okay, so we start off with our base file system, the base FS that we created with our MKOSI tooling. Then we layer on our configuration, we layer on our test, we layer on whatever the hell we want. You can just keep layering things on top of it to then execute later. And then we use the tool called systemd nspawn, which is another thing like Docker, except it's using systemd to create your containers for you. So this is where you pass in the base FS, right? And then your overlay FS. So overlay FS is the thing that's doing the layering. And then you get this boot option, and then bish bash boosh, we're now in a container. And we're running systemd. Like, guys, this is not a virtual machine. Listen, okay, I realize I'm way too nerdy for this. So I know. Like, this is cool. This is really cool stuff, right? It even says, you know, virtualization systemd spawn. But it's not virtualized. No, this is containered. So now that we're actually inside the container, I can actually run and do my thing that I wanted to do. Make run, create all my symlinks, do all my stuff, run all my testing. And nothing came of this, but it's cool nonetheless to see the A, B, C's, and D's and E's. But how does this actually work underneath the hood? So this is like the really complicated part of what Docker kind of gives to you with its file system layering. Basically what happens is systemd nspawn is going to first container itself. So it's going to create a new namespace called with the clone new ns, and then it's going to use that to set up the root file system and do all the overlaying. So it's going to remount its current your current root into a new one within this container with the I know we're supposed to be What I'm trying to say is that basically we create we basically create like a copy of root within this process, so that way this systemd process, this new container, can actually modify that root, but the host doesn't get modified while this is happening. And then we're going to start layering on top of our layering on top of that our other file system pieces that we want to kind of compose together, and then it remounts all this stuff. Blah, 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 and then we get into the overlay, which is now we're taking, to kind of take a step back a little bit, right? So we get our base image switched over to be basically the new root. So we're basically replacing things within our current host file system with the base image stuff. And then we're doing our layering, putting all of our composed file system, or our composed directories on top of that. And then finally, we do a pivot root, which basically does the actual replacement of the root file system with this new one. And then finally, at the end of all this, then systemd nspawn says, okay, now we're going to really container this thing. So now we're going to do the clone new user namespace, the new Unix timeshare namespace, the new IPC namespace, the new PID namespace, PID1, because this is running as PID1, and that's that. We have systemd running as a container. And the cool thing is if I go back to my host and I say, hey, look, I want to look for all the mounts with my name on it, and there's nothing there, but inside that systemd, there it is. Everything's all overlaid. So with this overlay, I could actually modify things on within that device, and it will affect my host because it's being overlaid on top of that. But it's still isolated in that those are the only places I can actually mutate files within the container that affect the host, right? So, takeaways. Docker does full isolation and containers on easy mode. We saw the syntax. That was really simple to do. Create your images, do your runs, bish, bash, boosh, there you go. Docker can be a burden for doing prototyping and testing. With the security put in place, you have to disable it, which is kind of unfortunate. So if you ever want to do your own sort of testing, have that isolation, be able to use your system to its fullest without being restricted, classic namespaces are the way to go. Any process can become a container. Okay, there's that interview question. Any process can become a container. You don't need to isolate the root file system necessarily. You can just run whatever you want within your container. Don't need to faffle with that. And then tools like unshare and systemd and nspawn also trivialize containerization with no code. We can learn more by looking at these links. Michael Karisk is the author, I think, of a lot of low-level system manuals, the manual pages. He has a really cool talk on that actually shows you step-by-step how to actually build and emulate Docker with just shell scripting by default. There's two of them there, so we have the C groups and we have his talk about the rebuilding Docker essentially, and then just to toot my own horn here, how I use containers to do this CVE back in 2022. All right, questions?
Fred, could you show us how to do that with FreeBSD?
No, but I can tell you. But I can tell you what they use. FreeBSD has its own containerization tool. I think it's called Jails. It basically kind of does the same thing as far as I understand, but that's about as far as I know about that. Otherwise, FreeBSD, I don't know if Mac is based off FreeBSD or probably not. It's probably just BSD, right? They do the whole virtualization and with Linux, and then do containers on top of that virtual environment.
Yeah, really, this is containers from scratch without Docker, basically. What about the number two out there called Podman? You're familiar with that one? Podman?
Yeah, no, tonight was, Podman operates essentially the same way as Docker. Yeah. So systemd, nspawn, Docker, classical commands, basically they all achieve the same thing with creating containers. The difference is maybe they might have different security policy, might be easier to use, not easier to use. There's like trade-offs to every tool in the tool chain with respect to that.
I guess Podman doesn't have, you don't have to have a daemon running to bring up your container, I guess. That's just what I've gained from reading a little bit.
Oh, okay, cool. Well, I had no idea. I never used Podman, so I had no idea.
Okay, thank you.
Hey, long-time watcher, first-time writer. Earlier we were containerizing or detailing containerizing of systemd, and it was then reporting when asked, and it says it was virtualized. Of course, I know the difference. And you said, no, it's not virtualized, it's containerized. What are the essential differences there between the two?
Okay, you want to know what the answer is to that interview question, is how I understood what you asked, right?
I've been doing web dev since I got out of school, and I would like to know more of the truth of the homeland. So if you could.
Okay, I'll give you the interview answer. Okay, I mean at least the short and sweet version, right? Right. So why systemd was reporting as being virtualized, I have no idea. I never looked into it. It doesn't really matter. But the key difference is virtualization. You're isolating essentially your kernel, your operating system, from other kernels and operating systems. So you can kind of think of one machine running many, right? Whereas containers is one machine running many processes like a normal computer would do, right? So if you open up Windows and you see all those tasks, things like that, basically those could all be containers in terms of Linux, right? Each of those processes could be their own container for all we know, right? So that's basically the difference. Process isolation and processes versus system isolation with virtual machines. Plus virtual machines, you get the added benefit of different architecture emulation, device emulation, all the fun stuff that you just don't have with processes on an x86 64 machine. So.
So you started out doing this for performance reasons, trying to analyze performance. Aside from the limitations you have with permissions, which is what led you down this road, did you find any extra overhead that tools like Docker had that you could bypass with this?
Yeah, no, that's actually a pretty good question. I don't know if I'm supposed to be repeating questions or not. I'm sorry for those that I didn't do that earlier too. But if I understand correctly, you're asking if running processes introduces any more significant overhead as opposed to not running containers?
Like if Docker has more overhead than your share-method,
Right.
companies that has more control.
Right. Okay. Okay. So Docker versus overhead versus process overhead versus what I've been. Very little actually. Once Docker has actually containerized the process, it's the exact same as what I was currently running. So the performance. So this is actually kind of like I should have mentioned this earlier too. Is that this is kind of like the benefit of containers, right? You can spin them up with the snap of a finger, right? Since they are just processes running on the machine, whereas virtual machines, now you have to set up your virtual memory mapping, you have to do all this other stuff, you actually have to boot up into essentially a brand new kernel to do virtualization. So there's more overhead with that and running in a virtual machine than there is running native processes on your machine as well, right? So that's kind of like the benefit of doing containers versus doing virtual machines is with the process isolation, you still have access to all your system resources. Obviously, you can limit them with C groups and things like that, but you still have access to these resources, whereas virtual machines do add overhead to your actual runtime. And if anything, if there's going to be any sort of performance penalty to doing my measurements with my particular problem, it would be the fact that I'm doing those measurements in the first place would actually introduce some performance penalty, but that's well understood, and has nothing to do with containers versus VMs. So yeah.
Any other questions? Going once, twice, give them a huge hand.